Welcome back to ELC 101. Hi everyone. This week we're talking about Chapter 10, which are control loops, controllers and final control elements, an overview of those. Basically, we'll be talking about all the different types of controllers that you may come into contact with. A lot of them are very well detailed. I would also look at that extra supplemental handout, which has all the different types of controllers listed, and you can take some extra notes as you're going along. It will help you to understand them. What we also need to look at is how these control loops work, what kind of action they have, and what their output will tell us, what they send for their output to the final control element. And we'll be talking about the different types of control elements that are out there, the final ones. So this is an example of our controller. So this is the controller. The information comes in. It's the process variable comes in that's being sensed, right? The process variable has a sensor and it's being sensed. It's matched to a set point and compared. There is an error that comes out of this. The error then is calculated upon inside the brains of here. This is the algorithms. The algorithms are P, I, or D, and we'll go into more detail in a couple of slides about P, I, and D, which I'm sure you've heard for your controllers. That calculates an output. Then the final control element is then acted upon and then corrected to send the signal to the final control element. So here, this is usually a control valve, but it may be some other pieces of equipment which we'll talk about. So it opens up or closes based on the set point to adjust that. Okay. This is the controller components and the front panel. This is an old-fashioned front panel. We have seen the front panel of the Yokogawa on our PC 101 trainer, and it doesn't really look like this. A little bit more difficult to configure, but again, that's what you'll have to learn going forward. But we'll just talk a little bit about the older ones. Again, all of these functions are in the newer ones. So you have an auto to manual switch. This is when the controller is either in these two types of modes. Manual is when you control it. You adjust the output, and that would be the valve, more than likely a control valve. Or an automatic, and then the controller itself controls the output here. This is just the set point adjustment. That's the set point over here. And then this tells you whether or not it's locally or remotely located. And then this is your process variable. And this again is the difference is calculated, and then the controller does its work inside its brains there. Okay, now just a review on manual control. Without automatic controllers, all the regulation tasks are done manually. So here, in this furnace example, if you want to, you read your temperature gauge. If the temperature is low and you want to fire up the furnace more, you have to come over here, you read the temperature gauge, and then you open the valve, which is the fuel supply, to get it hotter. If the temperature gauge is reading higher than it should be, you come over here and you manipulate the hand valve to the fuel and lower and close it a little. Okay, so again, it just depends on what you're doing out there. So this is another example. So you just have a straight line with no feedback, right? No feedback. Here's a transmitter, you read it, and then you adjust the valve. Automatic control, on the other hand, you're not here, right? You don't see yourself here. You have a transmitter, it goes to the controller compares set point and process variable, and then it manipulates the control valve. Another particular example. Here again, this is in the line, the sensor. It takes the sensor, then remember it converts and transmits to the transmitter, so we get this milliamp signal. So you take a real number range and convert it to milliamps, which we did on the last chapter. We talked about how to convert ranges to different milliamps. Goes as an input into the controller. The controller does those 3 C's. Compares, calculates, and corrects. It then sends an output also in a 4 to 20 milliamp to a transducer, which in this particular instance it's I, current, to P, pneumatic, 3 to 15 psi. And again, we talked about different conversions there and learning how to do 4 to 20 milliamps and 3 to 15. It sends that air, this is the hash line, means instrument air supply. It goes to the actuator, and the actuator then takes it and converts that to up or down pressure to control the valve. Closed loop feedback. Okay, and here again, this is just a summary again of that little bit of information we just talked about. Okay, now we want to talk about controller modes. This again is an old-fashioned type of side panel that is in your textbook. again, old-fashioned. You don't normally see this. If you look at your DCS or your controllers, this is all in the, you have to scroll through to find some of this information. And if you're at a DCS on your computer, you can click on the controller like FIC 302 and click on it, and you'll see all of these modes. We have a direct or reverse action on a controller, and then you can have the gain, reset, and rate. And these are all of the algorithms we've talked about, P, I, and D. All right, controller action first. Direct action means that the controller output will increase if there is an increase in the process variable. All right. Reverse action is the controller output will decrease if there is an increase in the process variable. So let's do two examples here. Direct action was the first one we talked about with temperature control. If my furnace temperature needs to be increased, I increase the output of that to open my fuel valve. Here we can look at level. If I'm filling a tank and my level goes up, I close my valve that's feeding it because I do not want to overfill it. Okay, so those are the two different types of situations. Now I want to talk a little bit about the actual controllers, and this is all in your text. This can get a little confusing, so we're just going to kind of talk a little bit about it and not really go into detail, and I'll make sure that whatever's on your test, because it will be open book, it won't be too difficult, but again, challenging enough. So P and ID, the control action settings, these are the algorithms, used to produce an appropriate dynamic response, meaning controlling the valve, to the process, resulting in a good or tuned control. Generally, we have instrument engineers and engineers will tune the controllers, but we are learning in this class and the next class that you can actually do that yourselves. You'll be learning how to do that. So the error is called the set point minus the process variable. So you read those two and then there's an error. The error is then fixed by these three ways. You can do it proportionally, which is your P, also known as your gain. You can do it integrally, which is your I, which is also known as reset. Or you can do it derivatively, which is D, which is also known as rate. So we'll go into detail each of them. Proportional is your first one. The input change of the controller required to produce a full range change in the output from the controller. So here are some definitions. The proportional band, that's what this PB is, in percentage, means it takes, if it's 100%, it means it takes the full range of your input to change the output of the controller through its full range. It's a one-to-one comparison. And there's some other math in here. I don't want to go into much detail right now. When we have some problems, and if we have a lot of them that have to do with a lot of the math, I will go over them in more detail. So gain, which is another term to describe the input to output relationship. When there's a change in the output, it is a change in the input. So that's defined as the gain of your process times your gain of your controller is always equal to 1. When we get into that in chapter 16, which is your next class, ELC 270, you'll see more of that. So you just kind of think of gain as a factor that describes how quickly or it'll compensate to make that change. Always done in 4 to 20 milliamps. Remember that when you put your output. Then on page 198 there are calculations to show how to get the process gain and how to get the controller gain. I'm not too heavily relying on that for this semester. Now we'll talk about integral and derivative. Integral action, I. It is designated to eliminate offset, which is inherent in feedback control loops. So for instance, you make an adjustment, right? The valve does the change, and then of course it may overshoot or may undershoot. That's this offset. So it's also known as reset. So what it does is it will repeat the proportional output, this gain, okay, as long as the error is still there, so many minutes per repeat. That's what the reset means. So it'll just keep doing it based on whatever the reset is that you put in there, a number you'll put in there. So it'll keep telling the controller to move the final control element by the amount of that gain in the P over and over until the error is gone. Okay, now, unlike the P mode, the gain, it is never alone, meaning you'll never have just an I controller. It'll be P and I, or it will be P, I, and D. Okay? Derivative action, D. This is known as the rate. It is equal to the rate of change of the error. So this may be used alone or usually in P, I, and D. And it's usually used in temperature loops. Again, you'll get to see these in later classes. All right, let's talk now about the different types of controllers. This is a local controller. This may be used, for instance, this may be used as a controller when you're doing a knockout drum to a flare tank. So this is separate, and again, if you have a plant that doesn't have a DCS system, you may see this. Okay, the remote controller is another controller that is actually just in another place, standalone. Now what happened is, in 1950s, when they've gotten really good at designing these control systems and DCSs, they made all of these the connections and the wiring all come to a main hub in the central control room, and now they're separated out so you keep it. Plus it's for safety reasons, and it is much safer to have them separated out in two different locations. This is a split range controller. Okay, so what happens here is this controller will do two different things. In this particular instance, we're looking at pressure. When you're filling a tank, one valve needs to be open to vent, right, to have the air that's being displaced. If you happen to be draining the tank, this valve is going to close, but you have to open another one, so it will allow it will fill it with oxygen so this tank doesn't implode. I want to give you another example of a split range control loop. Here, temperature control. You may have a jacketed in this particular instance, you have a cooler and a heater, right, for maybe heat exchanger, or it could be just controlling. This is a like blown up view of maybe a reactor. Okay, from 0 to 50%, you may be cooling it. Okay, and then from 51 to 100%, you may be heating, and that's what a split range does. So it just takes it in two different ways. It controls two different types of valves. So here, the temperature controller has one control valve here for cooling, and the other control valve, once you hit a certain number, for steam, for heating. Then there's cascade control. These are two or more controllers that are put together. All right, now another really good example for this is level control. You could just control level directly with this level transmitter, a level controller driving this valve all by itself. However, they generally set up level with flow as a cascaded loop. So the primary loop is the level control. It's called the master loop. The flow is called a slave. It's the secondary loop. So the level comes in to a controller. That output feeds as a set point for this flow controller, and then it controls that valve through that. So let's just understand why we do these two different ways. Cascade offers minimum operator intervention, minimum consumption of utilities. That's important. It's a quick response to process change. It's very stable, and it's a better way to control, and it reduces lag time. Here's another situation: manipulated stream versus controlled stream. So here they're talking about two different types of controllers again. This is the steam in, controlling the heat exchanger, and they want to just ask what is the type of control action. So we should be getting a couple of those questions in your homeworks. Okay, ratio control is used to ensure two flows are kept at the same ratio. So you may just feed one based on the other one. Okay, just it could be a 1-to-1. You need them to be exactly the same, or maybe you feed one in FT101 and FT102 goes in at half the rate, or it could be double. The ratio controllers are blending two or more flows to make a specified composition. Also for physical properties and so on, maintaining correct air and fuel mixture. You'll see ratio controllers definitely in furnaces as well. The feedback of a liquid level. Again, what type of control action? Just throwing these in there for you to look at, to be thinking about how you might use how the controllers might act. Would it be direct acting, or will it be reverse acting? Now we're going to talk about final control elements. This is the last active device in your instrument loop. It performs a manipulating operation on the process that brings about a change. There are three different types. We have your control valve, which is the one you see all the time. You could have louvers in a burnt furnace situation, and then a variable speed drive. So let's talk about the control valve. The control valve is the most common, and it is always the valve failure position is always determined for safety considerations. You have air to open and a fail close, and air to close and a fail open. So you just have to know which of the two or why they're used. The louver, again, can be opened or it could be closed to allow air into the firebox. The louver is just like blinds. And then finally, electric motors. This is a reversible electric motor, and it could be used to actuate like a block valve, just like a pneumatic actuator. Also, you can have a on and off level switch, say it says shuts the pump off maybe, or a variable speed motor to also drive it at different rates. Okay, so those are just some other types. All right, next we'll be talking about Chapter 11. We'll be talking about final control elements. Talk to you soon.